In today's episode, let's have a different take on acceleration, all right, and seeing how it will impact us if we don't go in a straight line anymore. So, classically, when we're solving these problems over here, we might end up using this equation like this. Acceleration is equal to v2 subtract v1 all over delta t, and crunching out the numbers, all right? So let's say that we have a vehicle that starts off at 16 meters per second, accelerates to 28 meters per second in the duration of 4 seconds. We go through the math, and that is our rate of uniform acceleration. All right. Now, how would we represent this graphically? Remember that any measurement that has a direction associated with it is a vector, and all vectors can be represented by drawing an arrow. All right. So we can solve these graphically. Two things to keep in mind. Whenever you deal with a delta v, or a change in velocity, as the formula is naturally a is equal to delta v over delta t, delta means a difference in. How do you find out the difference in height between you and your cousin? All right, you might have had to do this at every family gathering, and you probably hated it, just like how I would hate it as well. And what you had to do is that you would have to stand back to back with your cousin. Cousin will be happy. You will be disgruntled because you're the shorter one every single time. All right, and the difference is measured between the two heads. What you'll notice is that in order for that to be set up properly, both of you must be standing on the same ground, not like that, but level like this. All right. So you ensure that your tails are connected together if you are an animal, and then you measure the differences between the two heads. All right. So you always connect the vectors tail to tail, and your delta v is a comparison between the second object versus the first object. Always in that order. All right. If you flip it around, it's going to throw off your calculations. So it's always final subtract initial. Okay. Or object 2 or vector number 2 subtract vector number 1. All right. Let's apply these rules onto a number line since this is just one dimensional. Again, on these graphs, you always want to include a compass and a scale. And that's why they're known as scale diagrams. Okay. All right. So the first object is the same object. It was initially traveling at 16 meters per second, so that's v1, and then it was finally traveling at 28 meters per second, so you'd expect the vector to be a lot longer. When you place them down, make sure you connect them together from tail to tail. All right, and you want your delta v equation to always point to v2. So since v2 was the blue vector, or the longer one, you want your delta v vector to start from the head of v1 and point towards the head of v2. And it'll look something like that purple vector over there. And if you carefully measure out the length of this purple vector, you'll find out that that tells you the difference in the two numbers, which works out to 12 meters per second forwards. A lot of us end up stopping here and getting the wrong answer because we're not looking for the change in velocity. We're looking for the change in velocity over the change in time. We're trying to look for the acceleration. Okay, so we need to take this delta v now and divide it by our 4 seconds. And once we go through that, then we'll get the proper rate of acceleration. So whether if you approach this mathematically or graphically, you should arrive to the same answer. Think of another example that's like that. All right, this time around, I'm initially starting at a higher velocity and finishing off at a lower velocity. So this time around, we're going to have 16 subtract 28, which will give you negative 12, and negative 12 over 4 will give you 3 meters per second. But as a vector, never state this as negative 3.0 meters per second squared forwards. All right, that's grammatically incorrect. If it's a vector, you always want to make sure that your vector has a positive magnitude. Let the direction dictate, or let the vector dictate the direction. Okay. Now, if it's a scalar measurement, then obviously you have to leave the minus sign there because the minus sign means opposite of whatever the original direction was. It just wasn't given in the problem. Okay. Now let's approach this again graphically using the same exact rules. This time around, we start off with a longer vector and we finish off with a shorter vector. Yeah. So a longer vector was the red one, and we finish off with a shorter vector, which is the blue one. We still connect them together from tail to tail. And remember that the red vector was the first vector. All right. So when we draw our delta v, it must start from here and finish at the head of v2. And it'll look something like that. Yet again, we measure out the length of it, and this time around you can clearly see it's pointing towards the left, which is the opposite of forwards, and that's why it's 12 meters per second backwards. Finish off this problem by dividing by time, and there's your answer. All right, so you can take either approach, whether if it's mathematically or graphically, you should arrive to the same answer. So this is how you'd solve for it in one dimension, but how would you deal with it when it's in two dimensions? Okay, such as when you're going around in a circle. You might be familiar with the term uniform motion, and uniform motion means that you're traveling at a constant velocity or at a constant speed in the same direction. Uniform circular motion, on the other hand, is that you're just traveling at a constant speed, but you're constantly going around in a loop, all right, at the same radial distance away from the center of your rotation. For example, we have this car over here, and this car follows this path. Now, one interesting thing that you might note if you ever sat in a car and it's going around in a curve is that your body, for some reason, ends up getting lodged into the doorway. All right, if you're a passenger, then it's the doorway. If you're the driver, then you start moving towards your passenger. All right, and it's not that you are being pulled that way. A lot of us think that there's something that's grabbing us and yanking us there. Instead, you got to keep in mind that this car originally wanted, for example, over here, wanted to travel forwards. All right, so the velocity was towards the right. Okay. However, as you're turning around, the inertia of your body wanted to keep on going in that direction. However, it's the car seat and the car itself that's physically pulling you back into the center each and every single time. Okay. And that is known as the centripetal force that's pulling you towards the center, and that results in you experiencing a special type of acceleration, which is known as centripetal acceleration. Now, we're going to get through the proper formula in episode 1.18, so you can fast forward to that if you want to see that in more detail. But right now, let's just focus on average acceleration. All right, so this is like the precursor towards it, and it helps get your mindset set in a way that you can understand, why the calculations are what they are. Okay, and you've probably experienced this before, whether if centripetal acceleration, whether if you were in a car or even on this carnival ride, right? Where the moment that you, as a victim, enters right into here, you're greeted by a dude in the center who's all pumped up, has all the disco music going, disco, and initially, you're all chill sitting there, but then before you notice, just like these people over here, they're all stuck against the wall. All right. Now, the illusion that you have in your head is that there's something that's grabbing you and pulling you against the wall, and that illusion is known as the centrifugal force. It's not a real force, it's just something that's what you're experiencing because of your current situation, right? Because everything is all relative, right? So relative to you being in here, it feels like you're being pushed and crushed against the wall, where in fact the wall is helping you maintain this uniform circular motion. All right, and the only way for it to maintain it is to take you and constantly push you towards the center. And that's what centripetal acceleration is. Okay, so let's take this concept from a very basic principle from the idea of average acceleration. Let's say that you're this car over here, and as you're traveling, initially you are traveling towards the east. And at some point, you're traveling towards the south. Okay, and there's no exact detail of how you end up getting there. I mean, you could have taken this approach, you could have taken this approach. In fact, you could have taken a shortcut and just went there, and then suddenly when you open your eyes, you notice you're traveling southbound. All right, and that's why this is called average acceleration. You're not really seeing the details in between. Okay, so initially you're traveling at 2 meters per second towards east, you finish off at 2 meters per second towards the south, and that arc took about 1 second, or the full rotation 4 seconds. All right, and what is your average acceleration? By no means is this the same answer as what your centripetal acceleration will be, but again, we're going to save that for an episode 10 chapters down the road. Okay, so we're going to solve this using the graphical approach, as we've seen before, where you need to connect the two vectors together from tail to tail. All right, so we're going to take V1 and take V2 and connect them from tail to tail. When you're measuring out your delta V, that vector should always point where? That's right, towards V2. So it will look something like that. Okay, now in this example over here, it's a fairly straightforward one, as in it's a right triangle. And with our right triangles, it's fairly easy to find the hypotenuse. All right, where we're going to use simply c squared. Oh, I didn't do the calculation. C squared is equal to a squared plus b squared. Probably also want to label these out. There you go. So 2.0 meters per second squared plus 2.0 meters per second squared, which will give us 2.82 meters per second. There you go. All right. I guess, yeah, I didn't make space for that. You'll also notice that this vector is pointing in this direction over here, right? Where if north is up here, then this is south 45 degrees towards the west. All right, and how does this relate towards the original problem? Well, you'll see that initially you're traveling this way, and at some other point you're traveling that way. Okay, and we've just learned that if you're traveling towards the right, towards the east, and you're going around a circle, then your centripetal acceleration will be pointed towards the center. And if you're down here, your centripetal acceleration will also be pointed towards the center. Now, this is the world of average acceleration. So the average between those two would be exactly this. Okay, but remember that this is not the final answer, because that's just telling you your delta V. To find out your A average, you need to take it and divide by time, right? A is equal to delta V over delta T. Sub it in, crunch it out, and there's our final answer. Our rate of average acceleration is at 2.8 meters per second, south 45 degrees west. All right, and as I said, the number over here will not be accurate in accordance to centripetal acceleration, and that's because this is taking your average, where in some ways you're taking a shortcut. You're not going around the entire arc, you're just opening your eyes over here, then closing your eyes during your journey, and you're not opening your eyes again until at the end. All right. So for all you know, you might have gone around the curve, but you could have taken a shortcut as well and teleported. Okay, so it's not going to give you the accurate answer, but it's sufficient for at least tonight's homework. Okay, so here's a bit more challenging problem. We're going to solve it using a scale diagram first, and then we'll back it up with the math right afterwards. Okay, again, with these two vectors over here, we need to make sure that we connect them from tail to tail. So our first vector is 16 meters per second pointing towards the north, and then our second one is not necessarily pointing east or west anymore. Now it's traveling north 60 degrees towards the east. Making sure that we connect them together. Oh yeah, there's the animation. Okay, and now they're connected together from tail to tail. Our delta V must point which way? Towards this way or towards this way? Remember, it always needs to point to the second vector, right? So it must point in that direction over there. Good. Okay, so in this setup over here, north 60 degrees east, here's our 60 degrees. And with this, if you're drawing as a scale diagram, you can just carefully plot it out according to your scale. Take out your trusty ruler, measure out the length of it, and according to its scale, it works out to a corresponding velocity of 24 meters per second. Next, we take out our trusty protractor, and we measure from east towards the south. We find out that it's pointing at 5 degrees towards the south. Okay, and that's how you'd solve it using a scale diagram. You go off and draw it carefully as a scale diagram, and then you measure out your delta V. And don't forget, you need to also divide this by time towards finding it as an average acceleration. 24 divided by 4 gives you 6. So 6 meters per second squared, east 5 degrees towards the south. Okay, how would we solve this mathematically now? Now, some of you guys have probably figured and clued into this, that since V1 is a measurement, and V2 is also a measurement, and this angle over here can be determined based upon our givens. Anytime that you have a side, angle, side, you can use the cosine law towards finding out the length of the opposite side. Then, by using the sine law, you can find out the angle over here, adjust accordingly, and then you can figure out the direction that that vector is pointing towards. Okay, and yeah, let's go through that now. Okay, the same exact problem. We're going to solve it using the mathematical approach. And you can solve this either by the component method or the trigonometric method. All right. Trig method is with side angle side and cosine law followed by sine law. Component method, it's very similar to what we dealt with displacement. All right. You might be familiar with the displacement one, where your delta dr is equal to your delta d1 plus your delta d2. Okay, but this time around it's our delta v, and our delta v is equal to v2 as a vector. Subtract v1 as a vector. All right, and if we're solving this by components, well, then we need to break that formula down to its delta vx, which is equal to vf in the x dimension, subtract vi in the x dimension, and then we need to rinse and repeat in the vy dimension as well. All right, where vy is equal to vfy, subtract viy. Calculate them together, connect them together using Pythagorean theorem, find out the angle using inverse tangent, and then we'll get to our final answer. All right, so if you want to pause this video and work through it yourself, go ahead. Is that enough time? Okay, let's work through this together. Okay, as stated, this is our general formula. Delta v is equal to v2 subtract v1. We'll first solve it in the x dimension, and then we'll continue by solving in the y dimension. Okay, so our v2, the x component, let's take a look at this. Our resultant vector points upwards like this, and just according to how the angle is set up over here, we have our x component on the opposite side of 60 degrees, and we have our y component adjacent to 60 degrees. So when we solve for our v2x over here, we need to multiply v2 by the sine of 60 degrees. All right, so 28 meters per second times the sine of 60 degrees. As for v1, since it's facing directly towards the north, there is no x component. In fact, you could also multiply and calculate this out by multiplying it by the cosine of 90 degrees. Okay, and it'll, or sorry, yeah, the cosine of 90 degrees, and it'll give you an answer of 0. Yeah. All right. Okay, so we do the calculations over here. 28 meters per second. If you want to treat it as scalar as 28 meters per second positive, you can. That'll work out as well, and you'll get to the answer that's a decimal. There you go. We take this formula yet again. This time around, we're going to use the subscript y for the y dimension. So it'll look like this. And this time around, when we take a look at our v2, the y component that's right over here, it's adjacent to 60 degrees. So it'll be 28 meters per second north times the cosine of 60 degrees. All right, and we're going to subtract it from v1, which is also facing towards the north. Crunch it away, and there's our delta vy. We'll glue all of this stuff together by using the Pythagorean formula. Please don't use c squared is equal to a squared plus b squared, unless if you have a diagram that's already drawn. All right, then the reader understands where these letters are coming from. Without the diagram, you'll have to use the variables that are appropriate for this. For example, in this case over here, it's delta v is equal to the square root of delta vx squared plus delta v, oops, I got the colors wrong, delta vx squared plus delta vy squared. This color coding is just something that I've always used, where the red always were red right. That's why I use the x dimension in red, and anything that's in the y dimension, I use blue. Between the two, well, Roy G. Biv, green is somewhere in the middle. There you go. All right, no other signs other than that. Yeah, you do want to create some form of nomenclature for color coding in doing your notes. When I was in university, it got to one course where I had to deal with so many dimensions that if I wrote it out in black and white, I would not have any idea what I'm trying to solve at that moment. So I would just color code like crazy. All right, that way, when you have a whole page full of numbers and variables and equations, you know which section belongs with, which dimension and whatnot, and work through it that way. All right. Okay, so sub everything in, crunch through it. In fact, this is the hideous way of showing it. Anytime that you do an absolute value, you're really just getting rid of the vector and turning it into a scalar. So you could just simply get rid of those vertical slashes by getting rid of the arrow on top of the variable. Okay, sub it in, crunch it through, and there you go. That is the magnitude of delta v. As for the angle, you'll use inverse tangent. Okay, and How would you know which one to use? Well, it's based upon how you decide to set it up. Now, if you set it up using this method over here, then you're taking it that in your triangle, that this is the vector, and your Vy would be the opposite side. All right. So this will be the formula if your triangle was set up looking like this, as this is your opposite and this is your adjacent. Arctan is an old school way of saying tan inverse. If you are into software programming, you'll use arctan all the time in your coding, or atan. All right, because how do you do tan to the -1 otherwise, right, as coding? Okay, so yeah, you sub everything in, crunch through it, and then you'll get the corresponding angle, which is right over here. Now, as for your answer over here, it's not the final answer. This is just your change in velocity. So if the question asks, what is the object's change in velocity, then you finish off over here and you're done. All right, and you'll get your full marks there. However, if the question is asking what is the average acceleration, then you need to take this and divide this by the total time of the activity. Go through all that and you're good to go. Now, just to show you, do I have that animated out? Yeah. How do you solve this using the trig approach? All right. With the trig approach, first off, you need to draw a scale diagram. Then you use the cosine law towards finding out the length of the delta V. And finally, you need to find out the angle of this vector over here. Okay. Now, what will help us here is that if we take a look at angle A tells us the frame of reference relative to V1, and luckily V1 is towards the north. So in other words, whatever angle you have here, it's south, however many degrees towards the east. Okay, so you don't have to do any sort of compensation with regards to angle A after you solve for it. Okay, but at this stage over here, since we know our delta V's length and we know the angle, anytime that you have a side and an angle, you use sine law in solving for any other angle or side. All right, so angle A is over here, do your number crunching, and 85.32 is relative towards south, so there you go. There's your delta V, and here's your corresponding A average. And that's it for this episode. Again, for a more proper approach on centripetal acceleration, make sure you fast forward to episode 1.18. I'll see you then.